Hello student. Now we have another interesting problem. So now let me write down the problem. So again, okay. Here, actually let me make it small. Okay. xt looks like this one. So let me write down. So x, this is too thin. Yeah, so xt equals w t minus t over 2. Okay. Right? wt actually plus first. Okay, it doesn't matter, but anyway. Now this one plus wt minus t over 2. Okay. And then the question is, we want to calculate dxt, and then we want to prove dx naught, x naught. We have to prove. First, this part is easy to prove. Well, x naught is w naught plus basically 0 plus w naught. But again, w naught starting point of Brownian motion is 0, so it is t. So this is easy to prove. Right? This part is easy. So let's get this away. Now this part seems slightly more difficult, so let me use some trick that people like in this kind of problem. Trick is that w minus t to decompose this one into 1 plus e to the power of t, right? So multiply this one, same to this one, multiply same to this one, right? And then, well, let's use notation over here. So let's call this is we can decompose this seemingly complicated function into two parts. This is, let's say it is called as zt, and this is yt. Okay. And then we can write this one as first we yt and change of gt, and this one change because of y, and because it's stochastic process we have to up to second order, but second order there is no such thing, so dzt dyt, right? This looks very interesting. So we have slightly different notation over here, but I think you don't have to concern much about this one. So let's work on piece by piece. Let's calculate dz first and dy. So let's change it to black. So what is a dz? Okay, this one. Z is this one. So it's basically z e w minus t over 2, right? Which is first always ft dt plus fw dw, and then fww2 dw square, right? We have to do so. And then if we take derivative with respect to t, then what we have? If we take derivative with respect to t, well, we have minus half of t, half, and then, well, this is exactly the same, so dt dt, right? And then about second term, okay, if we take derivative t, you know, it is a kind of chain rule. It is same and t, so this one. And then if we take derivative with w, then we have a w term over here, and if it come out, then basically it is the same. So same, so this part is z, okay, z, so zt, dwt, and if we take derivative again, then basically we have the same thing, right? So w, so zt, but now wt square, right? Because because there is nothing over here, So if we take derivative of w, then, well, the 1. So again, take derivative again, you have same thing. So it is natural. Because it is not w term, this term doesn't affect anything when we take derivative in terms of w, the Brownian motion. And then because this is minus dt, so what we have zt dw plus half of zt dt. Okay, now let's compute dyt. Well, yt is simply the, right, it is 1 plus et. There is no Brownian motion over here, so we can just do simple differentiation. So it is et and dt, right? It is constant. You take derivative with t and nothing over here. So we have this one. So, and then the dy is simply, if we multiply, now we can multiply this one and this one, but this is basically 0 because dt, because dt square term is 0, and then dt, dw is 0, right? So it is 0. So we can just plug those equations over here. Over here, then we have, right? We have those things. We can collect terms. So dx, now we can collect. You can just plug this term over here, right? And this is gone. And then you can plug this one. Actually, plug this one over here, and then you can clean up. Then we will have this equation. Okay, we will have this equation. Zx, let me see. Yes, it should be something like this. So we are done. Okay. So this is a proof. Next, let's move to the next one. But actually, yes, I think there is a slight mistake over here. Yeah, dt. Yes, sorry. There is a. I have to divide it by 2 over here, and certainly there is no divided by 2. So this one goes out. So actually there is no such term. This should be gt dwt. Sorry. So yes. So actually zg, therefore dzt equals zt dwt. Okay. So I have to divide it by 2. So I forgot it. So we have this one, right? And dyt equal et dt, right? Et dt, which is exactly same one, and then all we have to do is plug this and this over here, then we are done. Okay, so sorry for my mistake. So this one should go here, and this one go here, and then we reorganize it, then we get this solution. Now let's go to the next problem. Next problem is very interesting. Next problem is that let x looks like this one. X is given by this equation. Then, sorry, let me hide this one. This one. Then use Ito formula. What we have to do is we have to use Ito formula to show that xt is martingale. Well, what is martingale? The definition of martingale is that the expected, the drift term, martingale is this is martingale. So x process xt is martingale. There is another way to define martingale, which is basically same to expectation of dxt is 0. So basically change. So for given time at the space time, the change of particle or xt is in expectation of 0. Then this is martingale. Okay, so which means that dxt, of course we can write this one as Ito lemma. So ft dt, fw dw, and fww dw square, and then we know expectation of dw because it's the Brownian motion. We know it is 0, which means that this is martingale, means ft dt plus fww 2 dw square, this term becomes 0. Okay, so let me show this one. W is martingale. So let's start on x. Okay, let me delete this one, and then xt equal, let me write down xt equal w minus t, right? W minus t exponential of w minus t over 2. Okay, so next take derivative with respect to t. If we take derivative, then, well, we have a solution over here, but let me do one by one. So if we take derivative first, let's take derivative of this one, this part, and leave as it is, and next we take derivative. So first we take derivative term with t, then we have a minus 1, and then we leave this term as it is, right? And then we take derivative with respect to t for this part. This part, now we have, because it's t, 1/2, so w minus t over t, but it is minus, it should be minus. Exponential of w minus t over 2, right? And then if we take derivative of w, well, this is tedious, right? This is very tedious. Exponential of wt over 2. And then plus, we take derivative of this one, so basically it's same xt, right? And if we take derivative again, again, then if we take derivative, then derivative with w, this one is the same. But if we take derivative, we come some again, so we have 2 xt, something like this. So let me check whether it's correct. W is, yeah, this looks correct. So xt. So we have to have this term ft dt plus dw square term should be 0, but this is dt, so we need to have ft plus 2 fww dt is 0, so then this is 0. So let's divide this one by 2, and then it is exponential of w minus t over 2 plus half of xt, right? So we can compare this one, and then we can compare this one, and then this one cancels out. Well, this term should cancel out as well because this part is xt. So cancels out. So we are done. So this is 0. So this is a martingale. This is martingale because expectation of dx is 0. Okay. If you want more explanation of martingale, you can maybe Google martingale. Martingale probability, Wikipedia. Yeah. Then there's some explanation about martingale, and yes. So this is alternative definition, but well, given this information, the new value is the same to old value, so the change between x and plus 1 and s1 is 0. So it is basically the same to my definition. Okay. And then there is example of martingale. That should be fun. So please read. You can read some of the examples of martingales. Okay. And then this is another one. Now we want to solve stochastic differential equation of this one. xt, dxt, xt, dw, t, xt, dt, and we look for a solution of the form xt exponential wt ft. And our goal is to find f small t, ft, this function. So basically we have to solve this function, and then in addition we have to have such that the initial condition is 0. Okay, so our strategy is like this. Our strategy, we apply E theorem over here. Yeah? And then, this one. Okay, and then we can match this one. So we have some solution over here, but I think because this is straightforward, so let me solve this problem in alternative way. Let me solve this problem alternative way. So instead of using this solution, please read this solution. This is another good way, but let me use slightly more complicated method actually to make you study. So let me take a slightly more complicated way to prove this one. So it is slightly more complicated, but it includes useful technique for stochastic calculus. So our original problem is dxt equals what? dxt is xtx dw. Actually, I can now, because you are now get used to it, let me just drop t. dx is x dw plus tx dt, right? It looks something like this. And then what we can do is let's calculate the log x. Okay, let's try the log x. The log x is of course this is a function of x, so basically log x, we have x, so there is no ft dt plus fx dx plus fxx to dx square. Okay, but here log x is fx, so ft is basically 0 because it is not a function of t, right? So this is gone. So this one, fx is 1 over x because of log x, and fxx is minus x minus 2, right? So let's plug this one. So x minus 1 dx minus x minus 2 over 2 dx square, but dx square is x plus dw plus tx dt square. So basically x square dw square plus something dt dw and plus t square x square dt square, but this is 0, this is 0. So we have only this term, which is now x square dt, right? So if we write down, it is the x over dx minus, well, it is 2x minus 2 x squared dt, so they cancels out. So tx over x minus dt over 2. Am I right? It should be. Yeah. So log x, so d log x equals dx over x minus 2 over dt. Okay, we show this one. Now, let's see this one. Here, now, our equation is x equal, let me use now blue color. Now, x equal what? Exponential of w plus ft. And our question is ft. Right, ft. Now let's take log because we have log equation. So let's take log. So log x is w plus ft, right? Now if we now calculate the log x, which is the log omega w ft. So it is ft dt, right? ft dt. Now the w is simply dw, and that's all, right? That's all. We have this one, and here, because x looks like this one, so x dw plus tx dt x over 2 dt. So this is cancels out dw plus t dt minus half of dt, right? Am I right? So it is dw plus t minus 1 over half dt. So now we match this one and this one, and then we are going to introduce this one. So now let me use green. So it means that ft equal to t minus 1 over 2. Okay? Yes? Actually f prime, ft, yeah. So we have the same one. Now we want to solve this one. And then the initial condition x naught equal to, given x naught equal to, right? X naught equal to meaning, well, here x naught, since x equals EWFT, so x naught is EW naught F0, which is 2. So this is basically 0. So F naught is 2. So which means that F naught is log 2, right? So our goal is now we have 2ft equal t minus 1 over 2, right? And then f0, and then which is log 2. And our question is, given these two conditions, what is ft? Right? And if we solve this one, we are done. So how to solve this? Well, this looks slightly complicated, but this kind of problem is called ordinary differential equation. Right? So in order to solve this one, ft equal basically df over dt, right? df over dt, isn't it? Which is t minus 1 over this one. So you can simply integrate. You can just integrate. You know how to do it, okay? So if you integrate, I assume everyone knows how to do the integration. So f is, if you do the integration, then basically it is the t, so half over t squared, t plus some constant, right? Constant. But now f0 should be, f0 is c, which is log 2. So therefore, our solution for ft is 2 over t squared minus half of t plus log 2. So this is our solution. Okay. So I took a slightly different approach. Basically, in my approach, I manipulated this part. But in this solution, they manipulated this part. They manipulated this part. Okay. And then this is not stochastic calculus, but in other problems, this is very frequently used. So let's review Leibniz integration rule. In calculus, Leibniz rule for differentiation under the integration sign is like this. So suppose, let me write down. Let me write down this one. So fxt, and here it is the integration with dt. Okay, but now integration is such that this is ax and bx. Okay, x, bx. Okay, so we want to integrate this f function, which is function of x and t, from a to b, right? Something like this. And then question is, we wanna take differentiation this one with x. How to do that? Okay, so Leibniz rule is that first, well, first what we need to do is, okay, because this part is slightly, as you change it, when bx increase, is slightly, integration is a size of area. So if we about this part tend to increase the size of the graph. Okay, area. This is if this increase, this decrease the size, right? So the intuition of the Leibniz rule is that, well, let me show the intuition. So we want to integrate from bx, ax, and this is fxt, and we want to do the integration, but we change x. So first, the first part is when we take different x, first when x change, because this part, this is not pretty. Let me change this one. Let me change this one. Let me clean up. Yeah. When x changes, multiple possibilities. When x changes, this one moves slightly, right? When x change, x plus dx, right? And then also when x changes, now this one moves this way, which is ax plus dx, right? And then of course, another one is that when x changes, this entire curve changes. This entire curve also changes, right? So this entire curve changes. So actually, this is not a good way. This entire curve changes. So this entire curve moves. Okay. Let me say maybe something like this one. So f x plus dx t. Okay. So about this part, when this part changes, so original integration is this area, right? This area is original integration. But when this part changes, about this part, this increase size of area. So how much? By this amount, right? And height is this point, right? Height is this point. So basically, this change by this amount, and this is the change is b prime x, okay, by change. And we need the plus because it increased size. And about height is this one, f px t, right? So that's why we have this first part, right? First part. And second part, now when x increases this part, now it decreases size this area. How much? The size is, height is this height is f ax t, and this is the change of x. So it decreases size by x, and the height is ax t. And the third part is now the change of this area. Change of this area is change of function. So this is change of function. So bx ax. Okay, change of function produces how much? This area. So change of this part f prime, right? xt dt. So this is a Leibniz rule. This is a very, very intuitive relationship. So this one, this is a proof. Now I got this one from very famous paper. So let me copy. Let me copy this one. And then open new one. Oops, what is going on? Yes, this one, and let me increase the size of this one. Okay, so suppose X, this is very famous paper, famous economics, from very famous economics paper. So let's look at X looks like this one, right? X, again. So here, let me write it down again. This is from very famous paper. So let's say xt is lambda, which is constant. So integration from minus infinity to t. And then e to the power of lambda t minus s cs ds. And then we want to calculate change of dx. Well, there is no stochastic term over here, so you don't have to use e to lemma. You can just take derivative with t. Okay? So how to do it? First we take derivative about this one. So use Leibniz rule. So first we take into account this part. So t. So now lambda, and then e minus lambda t minus s. But here s equals t, right? And then here, sorry, again, I forgot c. And then cs, but here s equals t. Okay, this is the first part. This is this part, right? This part. Okay. Now about second, this is minus infinity. So minus infinity, so it is constant. You can get a constant, so you don't have to take out of this part. And third part, this one. And then we have lambda minus infinity t, and we have to take derivative of this term. ds, right? First, let's take a look at the first part. This first part s equal t. So, well, this part becomes lambda e minus lambda 0 and ct, which is basically lambda ct. Okay, and now about this part. Let me use different color. Well, now we have to integrate this one. Look, but because it is exponential function, so if we take derivative of t, so this one is basically minus lambda e minus lambda t minus s ds cs ds, and then we need to integrate. We need to integrate this one over minus infinity to t, and then we have lambda over here. But remember this part is the same to minus lambda, and then e minus lambda t minus s cs ds, which is basically minus xt, right? Remember xt looks like this one, minus xt. So this whole part is minus lambda xt. So now we can combine this and this. So basically, therefore, d small x equal lambda ct dt plus this one, actually minus lambda xt dt, which is lambda c minus x dt. Okay, so we proved it. Okay, now there is another example. This again not stochastic calculus. This is not a stochastic calculus, and this is more of a standard one. But I think this is also useful. So if we have time, please go over this problem again. But to give you a hint, okay, I don't want to solve this problem for you. You can do this one yourself as a practice. You can regard this one summation as this integration as summation. Okay, you can regard this as summation, and then you can regard it as summation of this Brownian motion. And if you calculate it, I think you can do it. Okay, professor out.